This is following up on that work that we did yesterday, where we are graphing the exponential equations. Just this one includes a few more little details along the way. The parent function. Remember, the parent function is what we're left with when we strip away all the transformations. That's anything that might be multiplied into the equation or added into the equation. So notice there's going to be 3 transformations, but everything else is the parent function. You notice why I didn't put a box around is the 3 to the x. So the 3 to the x is our parent function. But then the transformations. Everything that I just put a box around represents a transformation. Now, in general terms, remember that any time we add or subtract, that's a shift of some sort. So then it's just a matter of knowing, are we shifting up, down, left, or right? But then multiplying. We haven't seen multiplying in a little bit longer. Multiplying, remember, is a stretch. Specifically, a vertical stretch by that factor. So when I go to describe the transformations in this one, that 2 that's out front is going to be a vertical stretch by a factor of 2. The plus 1. Notice the plus 1, by being in the exponent, it's with the x. And so if I add 1 directly to the x, that means that it's shifting it left 1. And the minus 9 hanging on the end, that does the same thing as what we saw yesterday. That's going to shift it down 9. And since it's shifted down 9, that tells us that our asymptote is at y equals negative 9. All right, and now it's time to put this into action in terms of making the graph itself. So the first thing we do is we draw on the asymptote, that dotted line. So that's the horizontal line down at negative 9. But then that first point, that's kind of the tricky part with this for some of us. It's saying that this is where we get the first point down here. So how do I know that is my first point? Well, normally yesterday, remember we saw that if I just moved it down 9, that was the only thing I had done to it, I'd be starting it up 1 from there. Because remember, anything to the power of 0 is 1. But I got a couple other transformations here. One of them is a vertical stretch by that factor of 2. Vertical stretch by a factor of 2 means that every point is going to be up twice as far. Now when I say up twice as far, I mean relative to the asymptote. So this distance here between the asymptote and that first point gets doubled. So instead of going up 1, my first point is actually up 2. Then notice I'm still not at where I put the first point. Why? Because we also, remember, are shifting it left 1. So I'm stretching it to start up at 2 instead. Basically, this number will always be our starting point now, how high above the asymptote we start. And then we shift left 1, so then that's how I then make that my first point. That first point, when you're doing an exponential, is the hardest part to get. Once you have the first point, it's actually easy from there. Because remember what a 3 to the x type of equation looks like and what that means. Yesterday when we did 3 to the x, that meant that as we went to the right, we were tripling our height. The same thing is true today. As I go to the right, I'm going to triple my height. So basically I can say, okay, well my first point is up 2. 2 times 3 is 6. So my next point then must be up 6. Remember, I'm counting from the asymptote here. I'm talking about a total height. And then that height gets multiplied by 3. Because whatever the last height was, I'm multiplying it by that number that's to the x. So what's 6 times 3? 18. Will that fit on my grid here? Yeah. Counting from the asymptote, remember? Yes. Because the asymptote's down at negative 9. And so if I count up 18 from there, that brings me up to a positive 9. So yes, it fits. Not by a lot. I don't have a lot of extra room, but yes, it does fit. Are there any more points that are going to fit on the right-hand side? No, definitely not, right? So then we go to the left. Remember that as I go to the right, I multiply by 3. So then as I go to the left, I divide by 3. So then I'm going to take each of my heights and I'm going to divide them by 3. So my first point, remember, that I plotted here was at 2. What's 2 divided by 3? Well, 2/3, basically. 2 over 3. So that's going to give me 2/3. Now, I'm going to estimate about where 2/3 is as I plot that point. No, you don't have to be perfect, but you should be fairly reasonable. We should be looking at something that's a bit below 1, but a bit above a half. So somewhere in there. And then I could keep kind of visually cutting that into thirds, dividing it by 3. But it very, very quickly, of course, gets to be like almost right on that asymptote. Once you find yourself plotting the points on the asymptote, you can go ahead and say, okay, now I know that the rest of the points are basically going to be right on it, and you can draw your curve. This is what you should be looking at then for your final graph. Notice the domain and range we get from that then. The domain is all real numbers because, of course, the domain is always all real numbers for an exponential. And then the range. The range here, y is greater than -9. Remember, not equal to. Because I can't ever actually reach -9 because that's where the asymptote is. And the asymptote is that line we approach but never cross and or actually reach. We're going to be dealing with graphing today, and I'm going to come back to it here in a little bit. But first, I'm also bringing your brain back to logarithms. We saw last week how do we convert between exponential and logarithmic forms. I would like you to practice that, please, by switching each of these into the other forms. Yes, use your notes, use the examples we did last week. So we end up using these notes that we took last week in order to be able to switch the forms around. So notice, like, if I'm going from exponential into logarithmic form, I'm saying I'm going from this into this. So the first thing I do is I write out log, always log, and then I write the b value. So then I go over to my exponential, I see, oh, okay, that's whatever's raised to the power, it's the base. And so in this case, notice the number that's raised to the power is the 6. That's why it's the 6 down there. And then the next thing I write in log is y. And I can see over here that y is the number that's by itself in the exponential. You notice that's the 36, so that's why I notice the 36. And then process of elimination tells you, but you can also just see over here it's x, which notice is the exponent. And so that's why it's the 2 there. And that's how we're using these notes, and we'll be able to fill in all of these. Here's the other answers. You should have gotten down that left-hand side then. As you work on memorizing this rule, again, the big thing to memorize at the very start is that log equals the exponent. So the one that's by itself should always be what the original exponent was. And then these are the rest of your answers that you should get down the right side. We do the exact same thing, just you're doing the process in reverse. You're just taking whatever your base is and raising it to the power of whatever log equals to get those new exponential equations. Just changing the form around. We're now going to take our knowledge about logarithms and start turning those logarithms into numbers that we couldn't find otherwise. So the first way we're going to do that here is a nice simple little calculation, log 30. So we're going to see how to do this on your calculator. So pull out your calculator and figure out what log 30 is. Now, how to do it? If you're doing it on a graphing calculator, you type it in pretty much as you see it there. You press the log button, then you enter 30 and press enter. If you're on a scientific calculator, in other words, a calculator where it's not just typing the stuff out as you type it in, you can see it on the screen. If you're doing it on one of those, typically your phone is one of these, then you would actually type in the 30 first, and then once you type in 30, you press the log button. If you do this correctly, you should be getting an answer of about 1.48. All right, so once you're able to get that number, then we can actually start taking a look at how to do this. But there's a little bit of a problem that we encounter here. Because you'll notice your calculator has a button that says log. It does not have a button that says log base 5. Now, usually what ends up happening then is somebody says, oh, that's easy. I'll press log, and then you press log and it gives you that parenthesis there. Okay, so I'll go log 5, and then I'll put in the 20. This will not work. What this is doing is this is calculating what log of 5 is, and then it's multiplying it by 20. That means something completely different than log base 5 of 20. Because remember, log base 5 of 20 is some unknown number that we're saying 5 to the power of what that would equal 20. And it's that exponent, that unknown exponent that we're trying to figure out. So that won't work. So what we have is we have a special formula that we're going to be able to use to calculate any logarithm value. We call it the change of base formula. So this is going to need to go into your notes. Put it with your other log stuff so it's all together and easy to find. But add this to your notes because we're going to then go back and use this to do that problem that we were just seeing. All right, and so this is a formula you're going to need to get to know, and the sooner you have it memorized, the better off you're going to be. So a little hint on remembering it. The thing that I always find helps is I know that when I read this, that I read it as log base b of y. Well, notice that the base is on the bottom of the fraction. So I always remember that the base goes on the bottom. That's how I remember it. Also, other people remember that the b here is lower. We actually physically write it lower when we write our logarithm. And notice it ends up being lower in the fraction as well. So that's another way you could remember that the base goes on the bottom as well. So now it's time to put that into action with our log base 5 of 20. So we know that in order to figure this out, that I'm going to have to do a log over a log. So then it's just a matter of which number goes where. Well, remember that the base goes on the bottom. The one that I write lower goes lower. So that means that the 5 must be the number on the bottom, which means the 20, of course, must be the number on top. So this is what I'm actually going to calculate. So take a moment, calculate what log of 20 divided by log of 5 is. And then check and make sure you're able to get the right thing out. You should be getting an answer of about 1.86. Once you can get that, then go ahead and calculate the rest of our values there for 3, 4, and 5. Now, if all went well on 3, 4, and 5, these are the answers that you should have found there. Number 3 is about 0.41, but 4 is actually exactly 0.75, and 5 is exactly 2.5. Yes, they work out to be nice, pretty numbers, and you can get into ideas of fractional exponents and stuff like that to actually explain that, but we're not going to worry about that part today. What I do want to still go back and worry about, though, is actually now thinking back to number 1. That's the one that we could just punch in the calculator and do. But what was the base there? I mean, when we press that log button, whenever we do log, it has to be log base something. There's always an assumed base. Well, just like all things in math, when we don't write it in, there is a number there that we just are skipping writing because mathematicians are known to be lazy. That number is actually a 10. The reason is because we live in a base 10 numbering system. Because we have the digits 0 through 9. We have 10 different digits. And so our numbering system is base 10. So when we do logarithms, we assume base 10 is there as well. This doesn't affect a whole lot, but it will affect a few little niche things. So you do want to make sure that you have this in your notes as well. All right, so looping back to our graphing piece, we are going to finish up today with looking to see how do we graph with a non-integer base, specifically fractions today. And so we're going to be graphing 1/2 to the power of x. Now, when we talk parent function, is there any addition taking place in this? No, so there's no shifts. I'm also not multiplying anything out front here. There's no negative out front or anything like that. So actually what we're looking at here is also another parent function. Because remember, our parent function is any number to the power of x. This is a number, 1/2, that's raised to the power of x. So our parent function is just 1/2 to the x. Doesn't matter that it's a fraction, it's still just a number to the x. Now because of that, because there's no transformations here, that means We don't list any transformations. And our asymptote is where? It's going to be at y equals 0, yes. And so in making this graph, then, the very first thing I want to do is I want to draw on that dotted line at 0. Do it on this one. I know it's tempting when it's on the axis to just say, okay, I'm just not going to draw it in here because it's assumed to be on the axis unless we tell otherwise. But I want you to be able to look back at this later and tell where it was. And I want this to be all super clear for you. Next up, it comes time to actually start plotting points. Yes, that means we have to do 1/2 to the power of something. But that's okay, we can do that. Like, what's 1/2 to the power of 0? 1, because remember, anything to the power of 0 is 1. The 1/2 didn't change that. And there was much rejoicing. Okay. So, that point, that's probably the easiest one. Okay, let's get a few more here. What about 1? If x is 1, what's 1/2 to the power of 1? 1/2. Okay, yeah, because anything to the power of 1 is just itself. So again, actually not too hard. Okay, great. We can do that. What about 2? What is 1/2 to the power of 2? Well, anytime you have a fraction and you want to square it, or actually any exponent to it, you apply that exponent to both the top and the bottom separately. So yeah, we're doing 1 squared over 2 squared, which would be 1/4. So our next point's at 1/4. Okay, what if x was 3? What would y be? Well, let's stick with fraction here. Well, that would be the same as 1/2 cubed, which is 1 cubed over 2 cubed, so that's 1 over 8. So it's 1/8. As I'm going to the right, let's actually now specify, because before we talked about how as we go to the right we're multiplying by this. As I go to the right here, what am I doing then?
Going down.
Yeah, we're going down, specifically by 1/2, right? You can describe that one of two different ways. You can say we're dividing by 2, or you could say we're multiplying by 1/2, but most people tend to think of it as I'm dividing it by 2. And so that gives me the points on the right-hand side. I can just keep cutting them in half all the way down, and eventually it ends up being like right on the asymptote. And what about on the left-hand side? Well, you might already be able to see the pattern, but let's actually do one of the problems to see. What is 1/2 to the power of -1? Well, remember what a negative exponent does to a fraction? A negative exponent flips. It flips the top to the bottom and the bottom to the top. And so 1/2 to the -1 is the same as 2 over 1, which is just 2. So then, when x is -1, y is 2. So what would 1/2 to the -2 be? Well, 1/2, I like to write it out because this can be a little bit tricky to see for some of us. Flip it, that uses the negative, so that would be the same as 2 to the power of 2. So it's 4. And so what would 1/2 to the -3 be? It would be 8. Notice what's happening as I go to the left. Most of us are going to describe it as we're multiplying by 2. Technically speaking, we're dividing by 1/2. But dividing by 1/2 is the same as multiplying by 2, and it's easier to think of that way. And so having plotted those points, we now can go ahead and sketch in our graph. So draw in your curve nicely and neatly, and then let's hit the domain and range. What is the domain of this equation? Yep, it is all real numbers because it's exponential. The fact that it's 1/2 to the x doesn't change that. It's still all real numbers for the domain. And what about our range? I like it. Our y values are all above the asymptote, and so it is y is greater than 0. Still greater than the asymptote. All right, now one last detail. This is the last thing we're going through today. There's a couple classifications given to exponential equations. And it's a differentiation between exponential growth and decay. This particular one is an example of exponential decay. Exponential growth is where it gets bigger as we go to the right. Decay is where it gets smaller as we go to the right. Basically then, you know if something's exponential growth or decay based on the base of it. In other words, what's raised to the power of x. If we're taking a number bigger than 1 to the power of x, we're growing, so it's exponential growth. If the number is between 0 and 1, like a half, it's getting smaller as we go to the right, and so that's exponential decay. Yes, this is good to put in your notes so that you remember it. A little note here, just because somebody probably is curious, what about the negatives? What do we call those? We do not do negatives to the power of x. We get into some really weird rules happening there because remember, like a negative squared would be a positive, but a negative cubed would be a negative, and all sorts of weird stuff like that. So we aren't even doing negative numbers to the x. So that's why negatives aren't even accounted for here.